I made a video in class during our lecture to show how to create these lens ray diagrams. And in class we got through the convex lens scenario where the object is further away and closer to the lens than the focal length. In this video, I'm going to show you those again because even though a few of your 7th grade colleagues were nice enough to let me videotape during their class, some of the footage just became a little bit muddled. You couldn't hear questions, for example, so to make everything easier, we're just going to go ahead and show everything from the beginning. And then we're going to show the concave lens scenario for objects that are closer and further away than the focal length as well. One of your sections actually got to this point, so this very much will be reviewed. All right, let's get started. So our first scenario, we have the convex lens where the object's further away, which we can see from the up arrow right here. And you hear me say in class a lot, what's the first line that we can draw with confidence? And that just means what behavior can we really predict. We've always started by drawing the first optic ray as coming from the top of the arrow. And we know that for a light ray that's coming in parallel to the optical axis, once it hits the convex lens, it'll be bent towards the focal point. So we're going to go ahead and draw that right now. I'm going to connect essentially this point and the point that we have highlighted on the arrow with a nice, hopefully straight line. We got there. There we are. And we know that it's going to be bent towards the focal point. So I'm going to go ahead and do that right now. I'm going to give myself a lot of space as well. I usually put a little arrow just so that I know which direction light's going in the diagram. Okay. The next line we can draw with confidence is the line connecting the top of the arrow and the center of the lens. And if you remember back from our cat picture warm-up with the goldfish bowl, we saw that the image of the cat was least distorted when it was going through the center of the bowl. And we're going to go ahead and assume that means that light doesn't really get bent at all if it's going through the center of these lenses. And that's actually what we do see happen in real life. A light ray that's coming from the top of this arrow to the center of this lens would actually go straight through without any change in its path. I'm gonna do my best to represent that now, like so, until they intersect. This is the point that I really want, because this tells me all the information really that I need. We could draw a third ray that goes to the center from the bottom of the arrow so that we know where the bottom of the arrow is going to exist. I'm going to go ahead and choose a different color here to show where the image of the object is going to be, and it's going to be right here. Okay? That's where the top of the arrow, or the image, I should say, of the top of the arrow is going to exist. That might be a little bit off here, but that doesn't have to be perfect, so that's okay. We can see this image is about 3 units on this square paper or graph paper, depending on what Mr. Norcross says for that. It's about 3 squares high, right? And we started with an image or an object that's 1, 2, 3, 4 squares high. You'll hear me ask this in class, what are 3 words I can use to describe this image? We certainly can say it's smaller. We can easily see that from the ray diagram. We also see that it is upside down, right? Another word for that we talk about is inverted, okay? So this is an inverted image that's being produced. And lastly, we know this is a real image. Now, a lot of you are catching on, which is great. When you create these ray diagrams, that's when we can tell if an image is real or if it's virtual. If it's real, we know that the light rays actually are crossing in real life. So if I had a laser, I've drawn this with red to be suggestive of it being the lasers we see in class, but these are the actual paths of light to create this image. So we can see light rays either going through the lens and bending down towards the focal point or going straight through the center and not changing at all. For virtual images, that's not the case, and we can actually look at that for this next construction, where the object is closer to the lens than the focal length is. So I'm going to go and scroll down, and we're going to look at that together really quick. Here we have the convex lens, the object closer to the focal point. First line I'm going to draw in red is connecting the top of the arrow to its parallel point on the lens, and that's parallel to the optical axis. So I'm going to draw that really quick. There we go. And light behaves exactly the same way, even if it's coming from closer or further away from the lens than the focal length. So I'm going to go ahead and bend that towards the focal point right there. and draw that line right there. There we go. Okay. The next line I'm going to draw is the same center line, or the line that's going through the center of the lens from the top of the arrow. So I'm connecting this point and again this point. And let's connect those. Okay. Like so. By the way, if I'm going too fast, pause the video. Take your time. That's fine. That's the reason why I'm making this in the first place. We can see that these two arrows right here are never going to intersect. They are on paths that onwards to infinity will never cross. All right? But we still see an image when we look through a convex lens with the object really close. It's not like it disappears. And to construct that, we're going to trace back where it looks like this light ray is coming from. So I'm going to start with this one first. So I'm going to start with this arrow, and I'm interested to see where it's coming from. So I'm actually putting my ruler right on top of this ray, and I'm going to make some dashed lines or dotted lines here to show where that light ray is coming from. I'm going to do the same thing for that first ray that I drew to the point where they intersect, and of course they will, because they're just straight lines, and going in one direction, straight lines don't intersect. Of course, they'll intersect in the other. So there's my point of intersection right there. Excellent. And like I said, the bottom of the arrow is on the optical axis. Because light rays that travel along the optical axis will just keep on going, you can see that this is the actual path that the light travels. But really what we care about is where it looks like it's traveling. So I'm going to go ahead and do my dotted line, because this horizontal arrow still, it looks like it's coming from the left at some point. We can connect these dots here. So this is where the top of my image is located. The bottom is directly down. I'm going to go and draw my dashed line from my image just to distinguish that a little bit. We can choose 3 words to describe this, right? We know that based on the image, or based on the drawing, that the image is upright. So we'll write that. And this is in no particular order. Really, these are just the descriptors I want you to be familiar with. So we know that the image is upright. We know that the image is larger by a lot. And lastly, we know that the image is virtual. I remember back from the previous construction, it was real because the light rays actually overlapped, or they intersected according to the diagram. Here we can see that the solid red lines never intersect, but the dotted lines do. And because it appears that they intersect at some point further towards the left, but they don't actually intersect, we call that a virtual image. Let's move on to the concave lens constructions. Okay, for the concave lens, we're first going to look at the object further than the focal point. Same as always, the first line I want to draw is coming from the top of the arrow, and wherever it would intersect with the lens, if it were traveling parallel to the optical axis. If you want to make some type of node, that always is my first step. I think it should be yours too. Because it's a concave lens, light rays don't converge like the convex lens. They actually diverge. So we're going to draw this arrow going out in some way, but we're going to utilize our focal point that's on the left side of the lens to show us exactly where it's going to be traveling. So I'm going to connect this dot, I'm going to connect this point, I should say, with this point, and that will be the direction that my light ray is diverted to. So I'm not going to go too far out because I don't want to go into my other drawing there. And because I know already there's going to be an image that forms, I'm going to go ahead and trace this back to the focal point to show that light rays aren't actually traveling from here, but it certainly seems that way. Okay. The next line we're going to connect is the center of the lens and the top of the arrow, or top of the object. Any point where these lines intersect, we can count on an image forming. And we can see already that we do get an intersection happening right there. And as always, we have our light ray traveling from the bottom of the arrow along the optical axis to show us where the bottom of the arrow is going to be. But we can pretty plainly see it's always going to be somewhere along there. This is now my point where my image is formed, and my 3 words to describe this, can you, oh no, spinning wheel of death. A note! Okay, I'm going to keep recording. No, I'm not going to keep recording. Okay, I think we're back. Okay, so OneNote just crashed a little bit, but we're used to that. The three ways that I can describe this image now is smaller. We can see that just from looking at the image. So I'm going to go ahead and write that down in not such a comedically large pen style. There we go. So it's smaller. Absolutely. We can tell that the image is upright just from looking at the construction. And we can tell that the image is virtual. And we know that because the image is formed at an intersection of rays where one ray, yes, actually does cross that path, but it only seems like the other ray crosses that path when in actuality diverges off. Let's look at our last construction. That's the concave lens where the object's closer than the focal point. We should be pros by now, connecting first to the top of the arrow to the point on the lens parallel to the optical axis. And then, oh, I've drawn the wrong thing. Let me go ahead and erase that without breaking OneNote. So we know it's going to diverge. Again, I'm going to connect my focal point to that point on the lens where that light ray connects from the top of the arrow. And that's going to diverge out. But it's also going to, I'm also going to trace back, I should say, where that light ray is supposedly coming from, but we know it's not. And I'm going to draw the next ray going straight through the center of the lens from the top of the arrow. And lastly, just really quickly, this ray that's coming from the bottom of the arrow. So our image is there, right here. We can see that. And curiously enough, it looks similar to our descriptions of the previous scenario, right? It's also upright. The image is also smaller, right? And our image is also virtual. Okay, so we can see here that there's a parallel between how lenses and mirrors behave. In particular, these are the same descriptions, so these right here, these are the exact same descriptions that we used for the convex mirror. So that's one way that you can start to see a parallel between how convex mirrors and concave lenses behave, but also how concave mirrors and convex lenses behave. I think I said that right. I should have written this down first. But either way, that's how we can construct these four scenarios. Now, your book goes through just describing what the image looks like for each scenario, but like I say in class, knowing how these are constructed should help you understand a little bit more why we say something is virtual, or say something is real, or say something is inverted, or say something is right side up. I hope you enjoyed this video. Please email me if you have any questions, and if you're watching this over spring break, I hope you're having a good time. See you when you get back.